In this video, we will look at an application of all we've learned about linear differential equations, including homogeneous equations, complementary functions, auxiliary equations, and particular solutions. You might see damped harmonic motion introduced through the mechanical system of a mass attached to a spring. We will start with this, but then also introduce similar systems in the realm of sound. We will start by assuming the motion of the mass on the spring is vertical and that positive direction is downward. The position of the mass at time t will be y of t, and equilibrium will be y equals 0. When the mass is set in motion, the forces that are at play are the force due to gravity, the spring force according to Hooke's law, the damping force due to friction like air resistance, and any external driving forces. Using Newton's second law of motion, the differential equation for this system is m times y double prime plus c times y prime plus k times y equal capital F of t, where m is the mass of the object, c is the damping constant, and k is the spring constant. If we consider the case where there are no external forces acting on the system, then we are considering the homogeneous differential equation my double prime plus cy prime plus ky equals 0. If there is no friction, meaning if c is equal to 0, then the differential equation becomes my double prime plus ky equals 0, which yields solutions y of t equals c1 sine of the square root of k over mt plus c2 cosine of the square root of k over mt, or simply y of t equal a naught cosine of square root of k over mt minus phi, where a naught is equal to the square root of c1 squared plus c2 squared, and phi is equal to the tangent inverse of c2 over c1. This solution was first introduced to us in trigonometry, and it describes simple harmonic motion. We've discussed this in another video where we represented the solution with a sine wave. We can hear these sine or cosine waves with an electronic oscillator. The amplitude is a naught, the frequency is f equal to 1 over 2 pi times the square root of k over m, and the phase shift is phi. One thing to point out with simple harmonic motion is that the wave will continue infinitely as time goes on. When c is not equal to 0, then we have a damped system. The homogeneous differential equation then leads to the auxiliary polynomial p of r equal m r squared plus cr plus k, which leads to three cases that come from the three possibilities of the discriminant c squared minus 4mk. They are listed here along with the real solutions we learned from linear differential equations. In each case, the solutions approach 0 as time tends to infinity, which gives insight into the use of the word damped. In the overdamped and critically damped cases, no indication of oscillation can be detected. But with the appearance of the sine and cosine function in the solutions, the underdamped case does indicate oscillation. In fact, this oscillation is between the curves y equal plus or minus a naught e to the negative ct over 2m, where a naught is the same value used in simple harmonic motion. If you are familiar with a piano, you know that there is a key that moves a hammer that strikes a string. But there are also dampers that are on the string, which only move away from the string when a key is pressed. If you hold the sustain pedal with your foot, then all strings have their dampers removed, and when one key is played, all strings on the piano will resonate. We discuss all of this by continuing on with forced harmonic motion. Forced harmonic motion is the case where there is an external force acting on the system. We stated the differential equation for this case earlier, my double prime plus cy prime plus ky equal capital F of t. We will consider periodic external forces, so capital F of t is equal to f naught cosine omega t, and we must consider whether the system is damped or not. If there is no damping, then again we have the case where c is equal to 0, and so my double prime plus ky equal f naught cosine omega t. The homogeneous differential equation results in the complementary function yc of t equal a naught cosine of square root of k over mt minus phi. We then need to find the particular solution, which depends on if omega is equal to square root of k over m or not. If omega is not equal to the square root of k over m, then the particular solution is yp of t equal f naught divided by k minus m omega squared cosine omega t. The general solution is simply the sum of two cosine waves, so the solution will always oscillate as t tends to infinity, but the amplitude is bounded. A very particular case of this is when the frequencies of the two cosine waves are very close to each other, which is discussed in another video on frequency beats. You can hear this with two oscillators tuned very close to each other, and it is used by piano tuners who listen to the beating between a string and a tuning fork to tune a piano. If omega is equal to the square root of k over m, then the differential equation is my double prime plus ky equal f naught cosine of the square root of k over mt, with the same complementary function as before, but with particular solution yp of t equal f naught divided by 2 square root of mk t sine of the square root of k over m t. The general solution is as follows. The difference with this case is that while there is oscillation, it is unbounded as t tends to infinity. When the natural oscillation of the system and the oscillation of the driving force are equal, in this case, we get what is called resonance. Resonance can be beautiful and it can be destructive. Beautiful resonance is found in musical instruments. Each instrument has its own natural oscillation, but it cannot make a sound until an external force is introduced. The external force needed depends on the system. When we remove the dampers on a piano and strike just one string, all the other strings vibrate because of the oscillation of the one that was struck. We can hear sounds in a seashell because the wind is vibrating air in the shell and causing the shell to vibrate on its own. And it's the same vibration that causes the perception of sound in the spiral cavity of the inner ear. Destructive resonance can be found in the spring mass system. If the oscillations of the system and the external force are equal, eventually the spring will break. This kind of resonance was also the cause of the destruction of the Tacoma Narrows Bridge in the 20th century. Wind was blowing at a certain frequency, which caused the bridge to vibrate at its resonant frequency. Eventually the support cables broke and the damping was removed, which caused the resonance to increase and eventually destroy the bridge. And finally, when there is damping on the system and an external periodic force is acting upon it, the differential equation is my double prime plus cy prime plus ky equal f naught cosine omega t. In the under-damping case, using methods we've seen before, the general solution is as follows. We can see that as t tends to infinity, the complementary function will tend to 0, and the particular solution will continue infinitely. We call the complementary function the transient part and the particular solution the steady state part of the solution. We can hear this on a piano by striking two different keys at once, but only holding one down. The one that is not held down introduces a part to the transient, the initial strike of the overall sound, but the only part that stays steady is the string that continues to vibrate at a superposition of the two frequencies. We can find more examples of the kind of harmonic motion we've discussed here in pendulums, clocks, and tidal patterns. We can also find examples of dampening in resistors on electric circuits. And just like what we've seen here, there can be both beautiful and destructive results.